Hey there, chemistry students. Here we are back again. Big idea 1, and this time part 2. We're going to be looking at electron history and theory. So what went into the current model of the electron and the atom that we have today that gives us all the ability to do what we do and the predictions that we make. So we'll start back in the early 1800s with John Dalton. And he was the first to recognize atoms and name atoms as the basic unit that makes up all things. And he said a couple things. He said that all atoms will come together to form different compounds. For example, CO2, right? And so CO2 is 1 carbon and 2 oxygens. So he defined this idea, and he also defined the law of definite proportions, saying that carbon dioxide will have 1 carbon and 2 oxygens. As soon as you start to change it like this, if you change it to this, it's a totally different compound. And it will be now carbon monoxide, totally different properties, very, very different. He also said the law of conservation of mass, which says that these things are never created or destroyed. They're going to change and sort of swap parts here and there, but whatever you put in is what you get out. And all of our stoichiometry then is based off the law of conservation of mass. So then, moving on from there, we had Mendeleev. And Mendeleev came along in 1869, and he developed the current periodic table that we have. And so this is Mendeleev's periodic table that you see right here. And so you can see that he didn't have all of the elements, but what he started doing is he started grouping the elements in order and started grouping them also based off of their properties. And so he was able to do some pretty amazing things. Like some of these elements he didn't know about. And so what he would do is he would just sort of name them and make up a name for them and say, this one probably will have an atomic mass of 46. It'll probably be metallic, and it'll do this. It'll be fairly soft, conduct electricity. So that's, and then later on when they found them, the actual elements, when they were able to actually synthesize them or dig them up, his notes matched up almost perfectly to what was actually there. So his little table that he set up made some incredible predictions. And so we've just essentially expanded his table since. So that was Mendeleev. Next guy that came along was Thompson. And Thompson experimented with a thing called a cathode ray. And a cathode ray essentially shoots electrons through a vacuum tube like this. And this shows his experiment right here. And so, so what he proposed is that these charged particles that were flowing through were electrons. And then he also proposed that, that they had a negative charge, because what he did was he put a positive and negative end right here. And those things, they deflected toward the positive side. And you see, this is the beam of electrons, and it's going to follow the positive side, which means that it's negative in charge itself because it's attracted to the positive side. He sort of came up with an idea for the electron as looking like a plum pudding or a cookie dough analogy. And so the idea was that you had this kind of blob, and throughout it was these electrons that were sort of stuck in this this pudding model. So that was Thompson. After Thompson came Millikan, and so Robert Millikan was able to calculate the actual charge of an electron. So this is way, way, way back when, in the late 1800s. And he calculated the charge of an electron. This is his device that he set up. And so in order to calculate the charge of an electron, this is absolutely incredible what he did, is he shot oil, sprayed oil, and this oil was essentially charged oil. And what he would do is he'd set up an electric field right here, and some of that oil would float. All that oil that was charged would actually float. And so he measured the charge of an individual electron based off this suspended oil floating over a magnetic electric field, and looking at that with a microscope. Absolutely incredible. Just mind-boggling that he was able to set something up, and this is at a time when a lot of people didn't have indoor plumbing or electricity. And then who came along next was Ernest Rutherford, and in the early 1900s he took and did this experiment, which discovered that an atom was mostly empty space. And so he proposed that an atom had a positively charged nucleus that contained most of the mass, and it had the negative stuff around it. So if you look at his experiment right here, what he did was he took a device that shot alpha particles, and those alpha particles would go through this slit right here. He shot them through a super thin gold foil sheet. And here's what he found. A lot of those particles would go through and be slightly deflected, and some of them would bounce back. And so his idea was some of them are just going straight through this. They're not hitting anything at all. They're just, you know, they're mostly just going straight through. That's why you see this beam right here. Now some of them must be brushing up against something, and so they're deflecting slightly. Now some of them are hitting them direct on, but very few in comparison to the amounts that are getting straight through. So he said, you know, this must be just a bunch of empty space and something in the middle. That's what Rutherford proposed. And so then we came to the idea of the quantum theory. And so the quantum theory is essentially what we work with now. It allows us to predict everything that we have going on around us. Now, a couple of guys that made this happen were Max Planck and Niels Bohr and de Broglie. So Louis de Broglie, and actually another one named Werner Heisenberg. All right, so let's start with Max Planck. So Max Planck figured out that electromagnetic energy is what we call quantized, which means as energy moves within the atom. So if this is your atom right here, sorry about that. If this is your atom right here, the energy is going to move in jumps. These are all like jumps of energy jumps. And so it'll go from here to here to here, and then maybe back to here. But it never moves in a progression, right? It never moves in like a slow progression. It always moves in these little steps or increments. And he called those quantums. Now, Niels Bohr got on this idea, and he developed a model for an atom. And his contribution was that he said that the atom had a nucleus in the center and the electrons, so it had a nucleus in the center, and the electrons existed around that nucleus in set orbits, right? And so then what would happen is then within those set orbits, the electron would go from here to here, and then back and forth, or up to a higher energy level. But they would never be anywhere in between. They'd be either in this orbit or this orbit. So essentially they'd appear and disappear. And as they did, they would go up energy levels as they absorbed energy. And as they came down, they would give off energy in the form of light. And mostly he discovered this because of looking at light and seeing its color wavelengths. Heisenberg sort of further defined his idea, because this idea worked great for hydrogen, but it seemed to be confusing with other things. And Heisenberg said, it's impossible to know both the location and velocity of electrons. So his principle was called the uncertainty principle. And he said, we can't know that the electron is in this exact orbit. We can sort of define a three-dimensional area where it's probable that it could be at any one given time. But it's not possible to ever know exactly where it is. It's just got some probability that it's in this area. So that was his idea, and so then we came up with the orbitals that were, we had ones that were like more spherical or 3D, and then we had like dumbbell-shaped orbitals and such, where the electrons would exist in after Heisenberg. De Broglie said that these electrons themselves, they move in wave-like patterns, and so he developed a sort of theory of wave motion in electrons. Now all these guys came together and all of their little discoveries defined and established for us the current model of the quantum model of the atom. Real quick, going to show you this little video, and this kind of helps to understand like what is a quantum and what is that quantum model as far as the model of the electron goes.
And he had a really surprising and completely counter-physical idea, which was that there were definite states, fixed orbits that these electrons could have, and only those orbits.
Bohr said that when an atom was heated, its electrons would become agitated and leap from one fixed orbit to another. Each downward leap would emit energy in the form of light in very specific wavelengths, And that's why atoms produce very specific colors. This is where we get the phrase quantum leap.
If it weren't for the quantum leap, you would have this smear of color coming out from an atom as it got excited or de-excited. But that's not what we see in the laboratory. You see very sharp reds and very sharp greens. It's the quantum leap that's the origin and the author of that sharp color.
What made the quantum leap so surprising was that the electron goes directly from here to there, seemingly without moving through the space in between. It was as if Mars suddenly popped from its own orbit out to Jupiter. Bohr argued that the quantum leap arises from a fundamental and fundamentally weird property of electrons and atoms, that their energy comes in discrete chunks that cannot be subdivided, specific minimum quantities called quanta. And that's why there are only discrete, specific orbits that electrons can occupy.
An electron had to be here or there and simply nowhere in between. And that's like nothing we experience in everyday life.
Think of your daily life. When you eat food, you think your food is quantized? Do you think that you have to take a certain amount of minimum food? Food is not quantized. But the energy of electrons in an atom are quantized. That is very mysterious, why that is.
As mysterious as it might be, the evidence quickly mounted showing that Bohr was right.
So looking at this and trying to sort of get an idea of what this is. So the quantum theory centrally is just centers around this idea that these guys all put together. Max Planck figured out that energy is a product of this right here is his constant, the Planck's constant, and this right here is frequency. So for every frequency, there's a specific energy that it needs for it to make that jump. And without that quantum or that particular amount of energy, it won't go. And when it comes back down, as you saw in the video, it gives off a certain wavelength of light corresponding to that frequency. So we found that all different colors of light have their own frequency. And this is how things give off light. So any light that you see around you is a result of quantum leaps going in and out of an atom.